Okay, let me go ahead and start. So today we're going to kind of finish with the last piece of the puzzle for making our power supply, and this is the regulator that we're going to cover. Okay, so what is the issue that we have? The problem that we need to solve now is that our power supply is actually unregulated. So let me kind of draw what we have thus far. AC voltage source, transformer. So we're stepping the voltage down. After we step the voltage down, we need to then rectify it. And then to rectify it, we're going to use for ours and for the lab, we could use a half wave rectifier. We're going to be using a full bridge or a full wave bridge rectifier. After the full wave bridge rectifier, we then have our capacitor. We call this a smoothing cap in this application because we're basically trying to take that pulsating DC and we're trying to turn it into that hopefully small ripple voltage. And then we would go into the load. However, here's the problem. If we were to design this for something like a 5-volt system or a 3.3-volt system or anything that we would use, say, to charge a laptop or to charge your phone or to run our microcontrollers and run our FPGAs, the problem you're going to run into is that this voltage is going to dip up and down in relationship to whatever this does, right? So this is a fixed divide by something, right? Divide by 10 is what we used in the previous example. So whatever happens to this voltage, if 170 goes up to 180, then this is also going to go from 17 to 18. And similarly with our full wave bridge rectifier, we're going to always get that 1.4 volt drop from the two diodes that have to conduct during either the positive or the negative alternation. So you're going to always have a fixed divide by something, in our case 10. You're always going to get a fixed drop by 1.4 volt. And there's really nothing that's going to maintain a constant voltage here. So if you've ever been in your house and your AC kicks on, your lights dim, right? Or your wires are a little longer than usual, your voltage is going to go ahead and sag. So we're kind of at the mercy of everything that happens here. And so as mains fluctuates, V sub RL will go up and down. Okay, so, and the reason is we consider this to be unregulated power. Okay, so with this circuit here, we're going to always be at the mercy of what happens here. So we wouldn't be able to actually run a device off of this DC voltage yet. because like I said, if we design this to give us a 5 volts constant across our load, it's not going to be constant. As soon as your AC kicks on, your voltage here is going to take a dip, your device is going to power off, or anything that happens in the house is upstream of this is going to cause quite a bit of fluctuation over here. So we need a way to solve that problem. Okay, and the way we can solve that is by using a regulator. Okay, now the device that we're going to be using, these parts have been around for quite a bit. These are very common components that have been used for a while. We kind of call these jelly bean parts because you just see them in every single design. They've been with us for a long time. And there's a few different regulators that we're going to go ahead and look at. Okay, so we have the 78XX series. This is the 7805, the 7809, 7812, 7815. Okay, now the first portion, these first 2 letters refer to the fact that these are designed for doing positive voltage, and the last 2 digits actually tell us what voltage is going to be regulated on the output. So in this case, we have a 5 volt regulator. We have a 9 volt regulator. We have 12 volts, and we have 15 volts. And we're going to start off with this. Once we see how this is applied, we can move on to all of our other types of regulators. Now, when you go ahead and purchase one of these 7805, 7809s, etc., it's going to come in a package. It could come in many different packages, but we're going to go with the very common TO220. This refers to the package. And the TO220 package looks a bit like this. 1, 2, pin 1, 2, pin 3. V in, ground, and V out. And I have some examples over here. Here is my parts bin of different regulators. These actually all have different values on them. I mean, obviously many of them are repeats, but this is a TO220 package. Now, the TO220 package is just the case that it's in. It doesn't say what the part is on the inside. Inside the circuitry, I could make this circuitry whatever I want. Well, not me, but the manufacturer, right? So the manufacturer could go ahead and put anything inside of this package. This is just a very common package, and they use these for regulators, for different types of transistors, for, MOSFETs, lots of other devices that we haven't even talked about yet. once you go ahead and specify what the part number is that's on this, that's inside of this package, now we have a specific device that we're working with. And this, if I went ahead and said 7805, this would be a 5-volt regulator. So we'd have a V in, a ground, and a V out on these terminals of the device. Let me see if I can actually get the text to show. Oh, wow. I even pulled out a 7805. A little hard to see. Let me see if I can play with the camera just a second so you can make out the text on there. Oh, yeah. And shine some light. Okay, a little hard to see. But this one says 7805. This one actually says 7812. So this is a 12-volt regulator. This is a 5-volt regulator. Okay. Now that refers to the voltage that we're going to get regulated on the output. So let's see how we can connect one of these and actually make it do some work for us. Okay, so to use one of these devices, and there is quite a bit that's actually going on inside of it. If we get some minutes at the end, I'll go over what the internal circuitry looks like, at least from an overview, from kind of a higher level approach of how voltage is being regulated here. But let's go ahead and let's say we have a 7805. Usually we draw it like this. Okay, so over on the input over here, we're going to have our V in. Over on the output, we have our V out. And this is our regulated. Because it's a 7805, we're going to get a constant 5 volts out, as long as we pay attention to a couple of things that we have to do in this circuit. The number 2 pin will go to ground. 1 and 3. 1 will be our voltage input. And we have to go ahead and put some filtering capacitors on both the input and the output. Now, for a 7805 or for any of the 78XX series, whether that's a 9-volt regulator, 12-volt regulator, our filtering caps are usually specified as 1 microfarad on the input, 0.1 microfarad on the output. Okay, and so from here, we can go ahead and now drive our load. Okay, so regardless if this was 100 ohms or 1K ohms or 50 ohms, regardless of what the load does over here, remember, it's always the load that determines how much current is going to be coming through our device, IRL. It's the size of this resistance that determines everything else that's going on. That's a really important key point to keep in mind, because it's your device that determines how much current it's going to use. And it's ultimately your device that's going to be burning off the power. So the power dissipated is determined by the size of the load. Okay, so this guy's job is to maintain this constant regulated 5 volts regardless of what happens over here. Vin could be 6 volts, Vin could be 7 volts, Vin could be 8, 9, 10, 20 volts. It doesn't matter. This regulator is going to maintain a fixed 5 volts on the output across our load. Now, there are some rules that we need to pay attention to. Okay, so these filter caps need to be 1 microfarad or 0.1 microfarad. 0.1 on the output, 1 microfarad on the input. But we also need to maintain a higher voltage on the input than the output. So first off, Vin must be greater than Vout. And hopefully that should kind of make sense, because I'm never going to be able to regulate a voltage higher than what I got going in, right? If I get 5 volts going in, I can't make 10 volts out. Not with one of these regulators. There are ways to do that to boost the voltage. Those are more advanced power supply chips or designs. Those are much more advanced designs in order to boost the voltage up. But the regulator, is his only job is just to maintain this voltage over here. Okay, so Vin must be greater than Vout. By how much? Do we need to be 1 volt higher than 5 volts? So can Vin be 6 volts and this will work? Is it 2 volts that we need to be higher than Vout? Does it have to be 5 volts? Okay, so the voltage that we must be greater than Vout is referred to as the dropout voltage. Okay, so the dropout voltage, V dropout. Okay, I'm going to go ahead, and V dropout is also one of those values that will change a little bit on us depending on the use case and heavily dependent on which manufacturer and which 7805 and which type of device, etc., etc. As a general rule of thumb, I'm going to say 2.5 volts is our V dropout. Okay, 2.5 volts. So in other words, if we want this circuit to work, Vin must be greater than or equal to Vout plus V dropout. So for our specific case, Vin must be greater than or equal to 5 volts plus 2.5 volts. So 7.5 volts. As long as we are 7.5 volts or greater on our input, we will get a trusty and reliable regulated 5 volts on the output. This device is amazing. And when you see what goes on the inside, you'll really start to appreciate what this chip is really doing for you. It's quite impressive. Okay, so, our 1 microfarad, 0.1 microfarad filter caps on the input and the output, and maintain a Vin that's greater than Vout plus the dropout voltage, and you have a working regulator. That's really all you need to know about this part. Let's take a look at the data sheet. Whenever we're working with any part, the data sheet is what has all of the useful information. That's where I got that 1 microfarad and that 0.1 microfarad. So let's go ahead and open up the data sheet. I was actually looking at one of these just the other day. Okay, let me turn that off, and LM7805. I want the original TI datasheet. Texas Instruments. Okay, so let's, all right, first off, they tell us fixed output voltage regulator. We have an output, we have an input. Here are the different packages it comes in. It comes in this giant one over here. In fact, I have just for a size comparison over here. In fact, I think I have most of these packages laying around. There we go. You can see this is physically much larger than this one. And that's this TO-3 package. This is a really old package. Then TO220. Then you have these little surface mount devices. These two at the bottom are much smaller than the two ones up here. Now, with that size difference comes how much actual power the device can dissipate. So the larger the package, generally speaking, the more power that can be dissipated by the regulator. And we do have to dissipate some power. And I'll show you guys how to calculate that in a minute. Okay, for those filter caps, where did I get those values? Well, I'd like to say I got it from this data sheet, but apparently I didn't. Okay, so over here, input C1, they are recommending for this one, they are recommending 0.22 microfarads. And they're saying required if the regulator is located far from the power supply filter. So if physically the power, so the transformer and that smoothing cap and that regulator, if these are physically further apart, then C1 is not even optional, it's mandatory. We need that for the regulator to work. Same thing for C2. It says over here, although no output capacitor is needed for stability, it does help transient response. So if our load uses a little current, then uses a lot of current, then uses a little current, those are transients. Those are changes in the load. Those are changes in the current that's coming out of this device. So in this case, they are recommending 0.1 microfarads. Okay, so this is where things start to get a little gray, which is, well, do I use 0.22 microfarads? Do I use 1 microfarad? Do I use 0.1? Do I use 0.47? Do I use 0.22? Generally speaking, 99% of the time, you're going to be fine with just these two values. As long as we have some capacitance here that's around a value like this, and on the output, as long as we have some small amount of capacitance, this device should work just fine. Okay, now the truth about these values is if I show you one of these caps, and for something like 1 microfarad, you might have to use something like an electrolytic cap. The tolerance on these caps are plus 40% minus 30%. Plus 40%. I'm not making this up. If I say that this is a 10 microfarad cap, it might actually be 14 microfarad, or it could be 0.7 microfarad. Plus 4% minus, plus 40% minus 30%. So the tolerance on these guys is pretty murky in the first place. So 1 microfarad might actually be 0.7 microfarad. It might be 1.4 micro. We just need some capacitance over here. Yeah, sorry, somebody asked me, is the dropout voltage going to be given? Yeah, I gave that dropout voltage, 2.5 volts. We're going to take that for all of our regulators and make it easy. Depending on different use cases, your regulator might have a dropout voltage of like 2.3 volts. It might be 2 volts. To be in the safe mark, always, we're just going to take 2.5 volts as a general rule of thumb. That's what I will use for exams and everything. You know, I try to keep things straightforward. The 7805 versus another regulator has a little different of a dropout voltage. So just like the forward voltage for a diode for silicon, we always take it to be 0.7. We're going to do the same thing for this dropout voltage. Okay. And for that output cap of 0.1 microfarad, maybe we end up using a cap like this, or a cap like this, or you really want to get something large, something like this. These are older. Okay, so we should have two caps and maintain that V dropout, and we should be good. Okay, let me see if there's something else that I can show from the data sheet. Okay, so output current up to 1.5 amps. That is the max of this part. You won't be able to put out 1.6 amps. However, that's not the whole story, because it depends on the voltage difference between the input and the output. So let me show you how to calculate power dissipated by this regulator. So let's go ahead, let's set up an example. Let's do 9 volts in. And let's do 1 microfarad. Let's do this properly. 1 microfarad on the input, 0.1 microfarad on the output. Okay, without giving a value yet, here is my question for you. Is this going to work first off? Will we get 5 volts? What are the two things we need to make sure we're adhering to? Do we have filter caps? Yes. Okay, that's the first thing we need. What's the second thing? The dropout voltage. This is probably the most important part, and this is where most people mess up when they're using one of these 7805s. And in fact, if your 7805 is not working, more than likely this is the culprit. So as I said, V dropout is going to be equal to 2.5 volts. So is 9 volts greater than 5 volts plus 2.5 volts? Yeah, absolutely. 5 plus 2.5, 7.5. 9's greater than that. We're good. Okay, so this is going to work. How much current is flowing through this circuit? That's my question for you. type into chat how much current is currently going through this 7805 and through our load. Do I need more information to be able to tell you how much current is actually going through the 7805, through the load, and through ground? Yes. Okay. I need some info here. Okay. Give me a value. Give me a lowish value. Something, I don't know, 50 ohms, 100 ohms, 200 ohms. Okay, so we have a 200 ohm load. Okay, notice the relationship. V equals IR. Okay, notice the relationship. As the resistance goes down, current goes up. The whole goal of this guy is to maintain a constant 5 volts. Therefore, V sub RL is always going to be 5 volts. We're going to always have 5 volts across here. That's the whole purpose of this guy. He's supposed to maintain a fixed 5 volts across our load. So it's the value of our load that's going to determine what the current is that's going through here. So if my resistor goes down in resistance, 50 ohms, 10 ohms, current should go higher. And if my load goes up 1K, 2K, 100K, then current will go down, okay? Inversely proportional. So let's go ahead and let's figure out what I is for this circuit. I'm going to get rid of this question mark over here. Whiteout is my new eraser. Okay, so let's figure out what I is equal to. Of course, I is going to be equal to 5 volts divided by 200. 25 milliamps. Okay, where did this current come from? Didn't really come from this cap. It came from, oh. So it looks like the current is going through our regulator. Right? It has to. The regulator is controlling how much current is being delivered to this load resistance, right? In order to maintain a 5 volt constant value here, this 7805 must control how much current is being allowed to go through our device in order to restrict it such that we get 5 volts at this point, okay? This is how the regulator does the job of maintaining a fixed 5 volts, by controlling how much current is going through and ultimately being delivered to your device. Okay, so we know from this setup we have 25 milliamps going through our 7805. What is the voltage drop across the 7805? Notice we have 5 volts here, we got 9 volts over here. Four volts across it. Okay, so we have 4 volts across the 7805. We have 25 milliamps going through the 7805. Okay, so what's our power being dissipated? So power being dissipated by the regulator is going to equal I times V. It's our power equation, PIV, P equals IV. Well, I is equal to 0.025 times 4 volts. So how many watts is that? Hundred milliwatts. Okay, so you can see if this current goes up, obviously we're going to get more power being dissipated by the regulator. Similarly, even if the current stayed the same, if I increase this voltage, I'm going to develop more of a voltage drop across my 7805. Hence, I will also get more power dissipated. So there's 2 ways that I can increase the power being dissipated by this regulator. Okay, now I should say, ideally, we would like to have 0 power dissipated by this regulator, because in order for this regulator to do its job of providing a fixed 5 volts, it has to waste some power over here. And that power gets wasted in the form of heat coming off of this guy. And so this is a reason why when you see one of these regulators in practice, you end up seeing it with one of these large heat sinks. I'm going to see how many different types of heat sinks I have laying around. This is actually a different type of heat sink. Nope, that's a repeat. That's what I got. Okay, 4 different types of heat sinks. Okay, so if you try to do 1.5 amps, that you're going to get a lot more power actually being dissipated off of this. So even though It says up to 1.5 amps. Yeah, that's pretty iffy. That's maybe if I only have a 2.5 volt drop across my regulator and I have a very large heatsink, sure, you can get up to 1.5 amps. But my point is, don't think just because the datasheet says 1.5 amps that I can put 1.5 amps when I have a 30 volt drop across my 7805. So let's go ahead and let's look at this. Let's say I do have 1.5 amps going through this load. Where does that 1.5 amps comes from? Well, it comes from over here, from our power supply. Let's say I had like 20 volts. Actually, that's kind of reasonable. Actually, let's do 14 volts, something like a lithium polymer battery. I'm just going to call it 15 volts to make it easy. And we have 1.5 amps going through. Okay, so then the question becomes, how much power is being dissipated by the regulator? Well, that's going to be 15 volts minus 5 volts times the current 1.5 amps. Okay, so what's that? Well, it's 10 times 1.5 amps, so 15 watts. Okay, 15 watts is a lot of power. Your light bulbs are like 30 LED light bulbs are like 30 watts, but if you had incandescent light bulbs, 60 watts is an incandescent light bulb. That's a good fraction of an incandescent light bulb. That's hot. That's a lot of heat that has to be dissipated from my device. And then the question becomes, can my device even dissipate that much heat? And once you're past a large value like this, the answer is actually no. So can you do 1.5 amps? Yeah, if your power dissipation is low. How do you get your power dissipation to be low when you have a lot of current going through your regulator? That's by having a very small voltage drop across your regulator. So doing things like 20 volts to 5 volts is much harder than it is to do 7.5 volts to 5 volts. Does that make sense? Any questions thus far? Let me pause for a minute, ask for questions. Okay, so a 7809 would produce the 5 volt output, 9 volt output, right? I just did all the examples using a 7805, but we have access to a 7809, a 7812, a 7815. There's more variations on this idea. We also have negative regulators. We also have adjustable regulators. So ones that we can control what the voltage output is from that. In fact, I have an example of an adjustable right here. This is actually an adjustable voltage regulator, and by turning this variable resistor, I can control what the regulated voltage is on the output. This is a little test circuit that I'm making.
That circuit doesn't need a heatsink.
No, so this guy I designed to give me a very stable 1.25 milliamps. So this is very low current. Yeah, this is actually not really for, like, say, powering something, but for measuring and testing something. I'm actually going to use it in a future video. And in fact, I'm going to make a video on soldering up this prototype. If you notice, I did not make a circuit board for this. And I did breadboard for verification, but as far as the construction, I'm going to do this nice, pretty layout over here and solder everything from underneath. And I'm going to make a tutorial video on how to make these types of soldered prototypes and have them turn out and look good. Right, like this actually looks pretty nice right now. This is a good layout. I've been playing around with the layout for a little bit, and all of my components that I need for a very stable 1.25 milliamps leaving this is there. And actually my load is over here on this side. So if I want to set it up very similar to how we've been drawing the schematic, it looks like this. We have our load on this side. This is actually a precision resistor. The resistors you're used to seeing are those blue ones, the 1%. This is actually a 0.01% tolerance resistor. So this guy is 100 times more accurate to 1K than your blue 1K standard resistors are. And then I'm feeding a constant 1.25 milliamps through it, and actually I can adjust that a little bit for a couple of different currents. So it's actually a current testing type of a board that I'm making. But yeah, any other questions on these regulators? They're super useful. Let me also let me go back to that data sheet. Okay, so one thing to realize is parts like this, a company designs them for usually a specific application. We needed the job of voltage regulators, so manufacturers ran to the necessity and created many different types of regulators for this purpose, because this is such a necessary thing to do for all of electronics. And think about it, all of our devices need constant voltages. So this is really fulfilling a need. But then there's lots of other things that you can do with these types of parts. So if I go through the data sheet, here, first off, you can see they give you an outline of that TO220 package, and they show you pin 1 over here is the input, ground, and output. They show you all of the different packages. They give you all the different electrical characteristics. So over here is where I would expect to see my dropout voltage. Here we go, right here. Under these two test conditions, so this is the temperature of the thermal junction of a specific transistor inside of the regulator. If that is at 25 degrees C, and we have 1 amp leaving this device, our dropout voltage is expected to be at 2 volts. But it could be higher depending on different operating characteristics. So that's why I gave you a worst case of 2.5 volts. I'm going to recommend that you stay above 2.5 volts. because there's some other regulators that have a little higher than 2 volts. There's regulators that have less than this. But at the end of the day, what I want people to get out of this class are good rules of thumb that you can apply to your circuits in 346, 347, 447, 490, etc. Because everyone is going to end up using one of these regulators. I guarantee it. In 346 and 347, you almost guaranteed for certain you're going to construct something and you're going to want a fixed voltage. And so I want to give general guidelines that if we follow those good practices, we're going to have things that work. So always have that input filter cap, always have that output filter cap, and always abide by that 2.5 volt voltage drop, or I should say dropout voltage, and your regulator is going to work fine, I promise you. But if you want to get a little more specific, that's when you're going to have to dig into the data sheet and you're going to go, oh, well, I'm not actually 2.5. I'm more like 2.3. Is that still okay? Is that still okay? Well, at that point, go look at the data sheet. The data sheet's going to tell you, and it looks like, yeah, you will more than likely be okay at 2 volts. That could change on you. Okay, so they gave the typical. There's some other things that we could look at, like the ripple rejection. So this tells you actually how much of that ripple voltage you can get rid of and your device can actually reject. So there's a lot more stuff that is in these data sheets. But what I wanted to show you was, okay, here's a functional diagram for everything that's going on. You can see that this is actually a complicated little device. There is a good amount of circuitry that's on here. And if you wanted to know how it's going to specifically behave, you would have to reference this. Not only that, we'd have to completely understand all of this. Some things to note about this device: we do have thermal shutdown. So if the device gets too hot, it will turn off by itself. It actually measures the temperature, and when it gets above a safe level, it will shut itself down. We also have some short circuit protection, which is nice. So if you accidentally short out the output, this guy should shut off.
What's the capacitor for?
Sorry, what's up?
What's the capacitor for?
So the capacitor's needed for quite a few different purposes. You kind of I need to show the inside for the capacitor to even make any sense. The capacitor is needed there's a feedback loop that occurs where it's constantly sensing the voltage and adjusting the voltage. So I think next class, I'm going to do a little high-level overview of how this part works on the inside. And that capacitor is to help the feedback loop. At least the output is, as far as responding to those changes in current. The input cap is mainly to deal with a certain problem of parasitic inductance that causes the part to not have the current that it needs to operate. That's why they say required if the regulator is located far from the power supply filter. That's the word that's telling me what the purpose is. That's the sentence.
What about for the circuit that you were showing us?
What circuit that I was showing?
The other one, the one where yeah, that one. What are the capacitors for?
That's what I'm talking about. I'm talking about what these
Oh, yeah,
capacitors are for. So this
Oh, okay.
output capacitor is needed for stability of the feedback loop that this that causes this guy to work in the first place. So I'm going to actually have to show at least a high level overview of what this part does on the inside for this to even make any sense. I can probably explain the purpose for this cap here right now, which is if we go ahead and set up okay, if I set this up over here, you're going to go, first thing you're going to ask is, why did he just add an inductor over here? It's not that I wanted this inductor over here. We actually have a word for these types of inductors that just manifest themselves as a product of living in the real world. This is a parasitic inductance. And so when I have a longer length of wire, I technically have an inductor over here. It's not a very high value inductor. It's not like this inductor where I have a zillion turns of this really thin wire, but it absolutely does have inductance, and I have to live with that. And so the further that my device is from where the 9 volts is coming from, or in our case, when we're building up our power supply, how far away this is from that transformer. And that transformer also adds some to this parasitic inductance. Parasitic, because parasite sounds like a bad word, right? If you have a parasite on you, generally you don't want your parasite on you, right? So generally speaking, I don't want this inductance over here, but I have to live with it. Like, it's part of just having wires. If you want to construct a useful circuit, you're going to have to put some wires in there, and as a result of having those wires, you're going to have this parasitic inductance. Well, this parasitic inductance, as current goes through our device and through our load, we have this changing magnetic field. Whether we want it or not, we're going to have this changing magnetic field. Well, what that ends up doing is it prevents the current from changing instantaneously. So if our device used 10 milliamps and all of a sudden it now uses 50 milliamps, you would expect the current to change almost instantaneously. But as you know from what I said last semester in regards to inductors, inductors oppose a change in current. So although our current, who is dictated by the load, it's our load that that determines how much current is going through this entire circuit. If you think about this being a computer, sometimes it's executing a multiply instruction, sometimes it's executing an addition instruction. That's a whole nother set of circuitry inside the CPU that has to switch on and off. So our current is always changing. It's jumping all over the place. Sometimes it's at 12 milliamps, sometimes it's at 100 milliamps, sometimes it's at 2 milliamps. So those changes in current, we would like them to be instant, but because of this parasitic inductance that opposes a change in current, anytime we have a change in current, it's going to take some time for the current to change. The current cannot change instantly. And that's because this inductor's opposing that change. So how do you deal with this problem? And I will say this is a real problem that exists all over all of our circuits. Any type of digital device, especially that has large changes in current, will have issues with this. And so this parasitic inductance is causing this to happen. Well, what we're doing here is all of this, we're just starving the device. And so the 7805 will not be able to operate if it's being starved for the current during these changes in current. So what we do is we add this nice little bulk capacitance over here so that when things are good and constant, it develops a charge. So whenever we're at the flat points, this guy is charged up. But once we start to starve the device from the current, all of a sudden, the capacitor can make up for that difference. Okay? So we call this a decoupling or a bypass cap. And all of your digital devices, if you are in if you are in 262 and you're working with that 8051 board and you look at the schematic for that 8051 board, they're always going to attach ground and attach power, but what they're going to also do is and one of these might be 10 microfarad, and another one might be 0.1 microfarad. But what you're going to see is you're going to see some bypass caps being added in order to address this issue, because anytime I have a long wire on a circuit, I'm going to end up with this parasitic inductance, and that parasitic inductance is going to cause this problem as current changes. And so the whole job of this bypass cap is to fill in those times when our device is having its mood swings due to this parasitic inductance, right? Okay, so that's the whole purpose for this first cap. That one I can at least do some explanation on. On this other cap, it's going to require a little more understanding of what's happening inside of the part. Does that kind of make sense? I think bypass caps are a good thing to talk about because you will see these sprinkled around like seasoning in your circuits, and that's no joke. If I pull up any type of schematic, you will find these. And in fact, let's look at the schematic for the 262 board. You don't have to be in 262 to be able to follow this. What is it? It's the EFM8BB1 LCK. Schematic. Do they provide the schematic? Okay, I actually have the schematic on my desktop. Here we go. Okay, so this is the schematic for that development board. Let's look at power and ground. Ground is right here. And our positive voltage, our 5 volts, comes in on VDD. Oh, what did I say? Right? They put bypass caps everywhere. Okay? So this is to solve that problem of the parasitic inductance. Mainly, there's other benefits to doing this. Every single design, your digital circuits, you should be adding bypass and decoupling caps. So when I do a design, I go ahead and I design from a functional point of view, and then I go over the schematic looking for little problem areas. One of the passes that I do when I'm verifying a design before I get it produced is I go and I look at all of the power signals, and I make sure that I have some bypass / decoupling caps in on all of my digital devices. So if we have any other digital parts on this board, we would have some bypass caps there too. Here we go. We have some for our power supply. Well, that was going to be obvious because I showed those with the 7805. This essentially is the same thing as a 7805. Or at least very, very similar to it. This one's actually looks like it's producing 3.3 volts instead of 5 volts. Here we go. Here, this is another digital device. Where's my power and ground? Okay, they're calling it VDD over here. VDD, here we go. 0.1 micro and 1 micro, and they call it decoupling. Bypass or decoupling caps. Same thing over here, our regulator in, and then the V-bus, more decoupling caps over here. Okay, so very real problem, very easy solution. So this is why I say I go through my design at the very end and I sprinkle the caps across. Is there a hard science around it? As far as what values and how much I need, you kind of go by a rule of thumb of putting like a 0.1 and a 4.7 microfarad on every digital device, unless the manufacturer recommends something other than that, or if you measure and see something later, you might add that in. In fact, I came across this just last week. I was constructing, and I won't go into what the purpose was behind this one. You can see it's kind of a mess. I was constructing something over here, and I was measuring, and I saw that I was getting some very unwanted noise or spikes. Technically noise is random. This had a fixed frequency that I was looking at, but I could tell that it looked like there was an issue with not having any decoupling caps. So I went ahead and I added some, even though the manufacturer did not say that you should. And they gave no recommendations on that. And once I added it, all of a sudden my noise that I was looking at under my oscilloscope went like half of what it was before. And so then it became all of a sudden tolerable. And that is probably a result of having these long wires, all of them acting like inductors. But when I go to a more finished product, my wires all of a sudden become shorter. That's going to be less of an issue, but I'm going to put those bypass caps in anyways, and it's going to be even less noise than I measured, and what I measured was tolerable, so I should be in a really good safe place. And so that's how you want to kind of follow your designs. Just kind of an overview. sort of design for the worst case, and when you get to a more finalized product, then you can go ahead and you should be in a better place than before. So that's kind of my hope when you're designing things. Okay. So any other questions before we take off? Okay, so we're going to finish up the simulation portion of lab. All we have to do now is add that regulator. We already constructed the transformer. You should already have the full wave bridge rectifier. You have to add the smoothing capacitor, and the regulator comes next. So I'm going to go ahead and take like a 15-minute break here. I'll be back at 9:30. Go ahead and continue with the lab, just doing the simulation portion. Next class, I will construct the whole thing and we'll measure it on the bench. Okay? All right. Thanks, everyone.